Okay, so hello everyone and welcome for the talk of today. So today
Yes.
we have Professor Spenta R. Wadia from the Institute of Center for Theoretical Sciences from Bangalore. So Professor Wadia did his Bachelor's of Science from St. Xavier's College, Bombay. All of us might be familiar with the St. Xavier's in Kathmandu, but yeah. He did his Master's of Science from IIT Kanpur in 1973. Then he did his PhD from the City University of New York and his postdoctoral from the Enrico Fermi Institute from University of Chicago. His specialties lie in black holes and quantum mechanics. So this will be the talk for today, and I'd really like to thank Professor for agreeing to speak with us. And are we audible, Professor?
Yes.
Yeah.
Thank you.
So even before we begin this, I have one question, and like that's all because I really want to ask you that. So what this is initial, okay, what motivated you to like pursue physics, or even more specifically, what motivated you to pursue a topic like string theory? What motivates physicists to do this?
Okay. What motivated me to do physics? Uh, that's a very good question. Uh, I found it the simplest of the things I was studying, like physics, chemistry, biology, and it's only many years later that I realized that if you talk about the hierarchy of complexity, then physics is the simplest because its laws are very easy to state. And in a sense, it underlies all of chemistry, biology. And so perhaps that was the thing that attracted me, that the, there's something called the idea of a law, which is easy to write down and perhaps solve. And yeah, and I was very fond of mathematics, so it was a good combination.
Uh,
So that was the reason I started doing physics and mathematics. Yes.
that's a really good answer. So yeah, like Khavindra Dai, please.
Okay. Uh, hey everyone, I'm Khavindra Katwal. Actually, I'm a fourth year PhD student at New Mexico State University, the Department of Astronomy. Actually, I'm here, all of you to thank you for all for being here. Especially, I'm very thankful to Rakshit who organized this event, and very thankful to the professor for coming us and giving this beautiful lectures. So yeah, I really want to thank on the B from the NSRS, actually National Science and Research Society. We always want to encourage the people come and join, talk about the science. Yeah, this is what we are actually standing for. So yeah, thank you all for being here. Please.
Okay, now I think we'll let Professor proceed. So yeah, Professor.
Okay. All right. So let me start my talk. So I'm going to basically take you on some sort of a tour of this area which I have mentioned in the title, black holes, quantum mechanics, and space-time. So it'll be basically some sort of a historical review of the ideas starting from Galileo and Newton. Okay. So first, let me present to you the Newtonian framework of physics and the universal law of gravitation. So, as we know, Galileo was one of the pioneers of the modern scientific method. And the only thing I'll say here about him, there's a lot to be said, is that he discovered a new law of gravity. And the new law of gravity is usually illustrated by somebody dropping two masses from the Leaning Tower of Pisa in Italy. And Galileo discovered that gravity acts in the same way on all bodies, and they all fall in the same way, independent of their mass. So this is an extremely important law of nature, that what we call inertial mass, which appears in Newton's second law of motion, is the same, identical numerically, to what is called a gravitational mass, which appears in Newton's law of gravity. And this law is very accurately verified, and it plays a key role in Newton's theory of gravity, because, as you know, the mass of the object rotating around the sun, let's say the moon or the Earth or stars, that mass actually cancels out, right? And also forms a very important cornerstone of the general theory of relativity. So this is Galileo's law, okay? And then in approximately the 17th century, Newton established a framework of mechanics, actually, a framework of, in fact, all of theoretical science, and in which he just I can't read my slides. Just 1 minute. If I do this, the slide is not large enough, right?
I think
Yes.
it's a bit
Just
small.
1 minute. Hold it. Hold it. Hold it. Hold it. How about this?
Okay, no, that's good.
That's good. It's all
Yeah.
right.
Yeah, it's
Because
perfect.
the other way, I can't read the slides, so I can't give the talk. All right.
Okay.
Okay. So now we are at Newton. So all of this will look very trivial to you, but I think at
Yeah,
that time, to sort of say that it is possible to describe the motion of any body as a flow in time in terms of some one parameter, uh, uh, in terms of the position of the particle as a function of this one parameter called time. And so this is this simple drawing over here of the motion of a particle, and the motion can be completely described if you know these three coordinates x, y, and z as a function of time. We all know that. And the important point here is that according to in Newton's theory, time is absolute and the same for all observers. So coordinates may be rotated or moved with constant velocity. You move around. I mean, we usually take transport. We fly in airplanes or spaceships, but more or less our clocks all agree by and large. And so this is the idea of time, absolute time, which was introduced by Newton. And then in terms of this idea, you have the second law of Newton, which says that the force is the inertial mass times the acceleration, right?
Yeah.
And then there is the law of universal gravitation, and which says that if you have two bodies of mass m1 and m2, they attract, and the attraction is given by this very famous force law, this 1 upon r square force law, where you have the mass m1 and m2 over here, and this is the vector that actually directed along the direction of attraction between these two bodies. Okay. So the force acts, the important point, and this perhaps is the crucial point, the force acts instantaneously at a distance. Means if the body m1 is shifted a little bit, then immediately m2 will feel that shift. Okay. So this is the instantaneous nature of the law of gravitation of Newton. It's always attractive, unlike the electromagnetic force. And the force is equal to m1 times acceleration. So you see, I was telling you this m1 will cancel from this m1 if the gravitational mass is equal to the inertial mass. Okay, so that was the importance of of Galileo's discovery. And in this simple case, it leads to the famous elliptical orbits of planets described by Kepler. So this formulation, the Newton's second law plus the law of gravitation, leads to the laws of Kepler, or the description of the orbits of planets, or for that matter, for the motion of any two gravitating bodies in the universe. However, Newton was not very satisfied with this idea of instantaneous at a distance, and he had some premonition that there is a problem here. And of course, it's only a few hundred years later that we understood what that problem was. And so I'll come to that a bit later. But let me read out something from the Principia Mathematica, 1713. Newton says that I have not been able to discover the cause of these properties of gravity from phenomena, and I feign no hypothesis. It is enough that gravity does really exist and acts according to the laws I have explained, and that it abundantly serves to account for all the motions of celestial bodies. So he says he doesn't know the cause of gravitation, but it's enough that it exists and the laws describe what is experimentally observed. And I think this is a very profound statement, because it shows the importance of experiment that sort of imbibed in Newton's entire outlook on science. Actually.
Yeah, I think in 17, like now it feels very trivial, but in 17th century, yeah, but just to think about this and to realize this theory is somewhat flawed at an inner level, that's
right. That's quite amazing.
Yeah.
So now let's jump to the middle of the 19th century. A lot happens, but for this talk, I'll jump, and we'll now discuss electricity and magnetism. So this is another big revolution of physics. So let me just explain to you in one or two slides what this revolution was. So Michael Faraday had demonstrated that light is polarized by a magnetic field. So there is already a sort of understanding that optics has something to do with electromagnetism. So this is a very important experiment. And then there are lots of experiments which led to the laws of electrodynamics. And those laws were basically completed by James Clerk Maxwell in 1865. And those completed laws of electricity and magnetism made a very important prediction. They predicted the existence of electromagnetic waves and identified light as an electromagnetic wave of oscillating electric and magnetic fields moving at a certain speed c, which in vacuum, idealized vacuum, would be what we all know. It's approximately 3.1 times 10 to the 5 kilometers per second. And in this way, he unified electricity, magnetism, and optics. So this is the cartoon of a wave of light on the right side below Maxwell's photograph. So you see the oscillating electric field in red and the oscillating magnetic field in blue. They're sort of perpendicular to each other, and they are perpendicular to the direction of motion. And this is the description of light as a wave motion in Maxwell's theory of electromagnetism. Okay, so this is a very big step in the history of science. And I just wanted to point out to you that Maxwell looks here quite old, but you must realize that Maxwell's life was very short. He died at the age of 48 or 49.
And I think yeah, like such a great accomplishment, and like in some way, special relativity was kind of inspired by Maxwell.
I'm coming to that. I'm coming to that. Okay. So now the important point is that this is a theory, but it had a very important prediction, as I mentioned, that light is an electromagnetic wave. means the visible light. At that time, people knew only visible light, right? But in 1887, Heinrich Hertz discovered and demonstrated the existence of radio waves, that were predicted by Maxwell's theory. See, Maxwell's theory predicts the light of all wavelengths, right? Electromagnetic radiation of all wavelengths, all of them moving at the speed of light. But experimentally, one had only seen the optical wavelengths, right? The one we are accustomed to, or what we can see the world around with. But Hertz discovered radio waves which were 10,000 times longer. The wavelength is longer than the wavelength of light. And in 1895, Röntgen made this serendipitous discovery of X-rays, which are electromagnetic waves whose wavelength is 100 times shorter than visible light. So, this is like filling up the electromagnetic spectrum, the idea. So Maxwell's theory is amply experimentally verified. Okay, so that's very important actually, that there was a big theoretical unification which explains experiments. And so you can, whatever else it predicts, you should take very seriously. So the next big step after Maxwell's theory is the special theory of relativity. And it was Einstein and Poincaré and Lorentz that were able to abstract the implications of Maxwell's theory of electromagnetism for our idea of space and time. So this is a very important statement, that Maxwell's theory is known, is sort of verified experimentally. And it is these people, Lorentz, Poincaré, and especially Einstein, who understood its implication for our notions of space and time. Okay, and it's based on the following simple one-line principle, that Maxwell's theory says basically that the speed of light is the same, whether you run towards the source of light or you run away from it. Space and time have to adjust themselves to ensure this extremely important property. Yeah, so I mean, after the lecture and whenever you're discussing it, this statement is the heart of the special theory of relativity. You just need this to derive everything, actually. Okay, but I will not be able to do that for you. But this is the main point which comes from Maxwell's theory, because Maxwell's equations are invariant under, are invariant if you travel at some constant speed with respect to them. Means if you have an experimentalist working in some lab using Maxwell's equations, and you have some other lab actually, let's say in some spaceship using Maxwell's equations, then these two people, for these two observers, the laws of nature, the laws of electricity and magnetism are the same. And the speed of light, that constant, is the same. And this has an implication for space-time. And here is a very simple cartoon which I have over here to explain this point. So, I'm sorry, just a minute, yeah. So consider this, some astronaut traveling in a spaceship, okay? And that spaceship is traveling at a speed v, velocity v, because it's traveling from left to right. And there is someone on the ground observing this astronaut. Okay, and the astronaut has a timekeeping device inside the rocket, and that's some laser actually that keeps on bouncing. And let's say one bounce is 1 second or something like that, some unit of time. Okay, now how does the ground-based observer notice the fact that the light beam goes to a mirror and comes down? So this is what happens. So you see, this is the observer on the ground, and this is how she observes the light starting from the mirror below, going on top, and coming down. So the Earth observer sees light travel further clearly because the rocket is moving than the astronaut. Okay. So if you just do this very simple calculation, what is this distance? This is the distance traveled by light, right? So it is c times delta t prime. Delta t prime is something she is clocking. And this distance is v times delta t prime because this is how fast a spaceship is moving. And then this time is basically this distance is c times delta t because the light is thus bouncing here. And this is nothing but the simple triangle theorem that hypotenuse square is square of this plus the square of that. And if you work this simple formula out, you'll get the famous law of time dilation. So you see, there is nothing absolute about time. It depends upon the state of motion. So this is the first important implication of Maxwell's theory, that it has an implication for the notion of time. And this is the formula. So if v is very, very small, like the speeds that we live with every day, then clearly delta t prime is the same as t, delta t, right? But if the speed is very high, then clearly this factor goes to zero, the denominator, and therefore delta t compared to delta t prime compared to delta t is very large. So you have time dilation. It dilates actually. Okay. Now this type of effect is observed, for example, and very useful in elementary particle physics, because you can think about the measurement of the decay of a meson. Okay? And you can sort of measure its lifetime. And from the measurement of its lifetime and its speed, you can infer the speed of the particle basically. And from there, you can make an estimate of the rest mass of the meson. And this is a very important test of special relativity, which was, I think, first proposed by the Indian physicist Homi Bhabha, who was the founder of the Tata Institute of Fundamental Research in Bombay at that time. Okay. So, is this clear?
Yeah, it is clear. You can proceed.
Okay. All right. So the next big step comes is the step of geometrizing the idea of space-time mixing. Okay. So I showed you that space and time are not absolute, but they mix into each other. I didn't do it in detail, but indicated, at least for the idea of time, that it can dilate, shrink, or expand depending upon the state of motion. And here I have the next slide explaining to you that Hermann Minkowski introduced geometry in special relativity, and this is a very big step. And in his own words, he says, henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. It's quite amazing. So what he did was, he realized that in analogy with Euclid's geometry, you can write down the distance between 2 points very easily by the triangle theorem, right? And so you have, if the points are very close by, then the infinitesimal distance square is equal to, let's say, dx4 square plus dx square, right? Now, what Minkowski realized is that if you change the sign from plus to minus, this is the invariant of the special theory of relativity. Now, why is this dx square equal to dx4 square plus dx square, dx vector square important? An idea is because it tells you that this object dx square is invariant under rotations, in space, right? In a space which is given by the coordinates x and x4, if you make a rotation, ds square is invariant. So what Minkowski said is that the analog of this for special relativity is simply to change the sign. So the sign of the time interval square is different from the sign of the space interval square, and there's a minus sign in between. So this is the important point, that Minkowski realized that special relativity can be sort of encapsulated in geometric terms, in terms of this very simple and beautiful idea. And so this distance square, which Minkowski wrote down, is invariant under Lorentz transformations. Okay, so I just wanted to introduce to you the idea. See what we have done. We have started from Maxwell's theory. From Maxwell's theory, what are the implications for our ideas of space-time? Then our ideas of space-time, how to geometrize them. And that is where we are at the moment, okay? So the next step is general relativity. So between 1905 and 1915, you have these 10 years during which Albert Einstein thought about the paradoxes special relativity raises for the theory of gravitation. And the paradox is very simple. As I said in the beginning, that Newton's law of gravitation assumes that the interaction is instantaneous, right? That means whatever is causing the interaction is moving at infinite speed. However, Maxwell's theory says that the speed of light is finite and the same for all observers in relative motion. So there can be no action at a distance which is simultaneous for all inertial observers in relative motion. So the idea of simultaneity is gone with special relativity. What is simultaneous for you may not be simultaneous for somebody who is moving with respect to you. Okay. Hence, Newton's law of gravitation needs to be modified. Now, I mean, I'll just read out what I wrote because I've studied this history also. Waging one of the great struggles in modern scientific history, in 1915, Einstein completed the general theory of relativity, which is a theory of gravity in which the force of gravity is not instantaneous. It is communicated at a finite speed, c, the same speed as the speed of light, by changes in the geometry of space and time. And here, the role of electromagnetic field is played by the metric of space-time. The metric of space-time tells you how nearby points are related, actually. The ds square has that metric. Okay, so here is a simple sort of one slide on pictorially what is the general theory of relativity. As I said, GR describes the changes of the geometry of space-time caused by a massive object in which other objects move. For example, in the Newtonian theory, the sun is a big object. It has a gravitational field and the planets move around it in the gravitational field according to Newton's laws. But general relativity says that the space-time around the sun gets warped, gets curved. Space-time, not only space. It's very important. And what you have is something which I just took out from. There are lots of animations here which are from many friends of mine who have given talks and who are very good at making animations. And I think this most of them are due to Juan Maldacena. What I just wanted to say is that this is a cartoon of a sun, of our sun, let's say, a huge object which curves the space-time around it. Now, this is just a picture of it. It's like if you put a very heavy ball on a trampoline, it just depresses, right? And then if you have a smaller ball at the edge and you leave it, it'll just fall towards it, right? So this is the idea that this small object that, just one minute, this object is moving around. It's moving around. It's responding to the curvature of the geometry. Okay? And that is the new law of how particles move in a gravitational field due to Einstein. Now the point is that you might be wondering, I don't see any elastic grid of space-time, or we have never observed anything like that, right? I mean, we have observed electromagnetic fields, in space-time. We can measure them, we can understand them, but we had not seen for a very long time, till 2015, the vibrations of this grid. And I'll come to that later, because these vibrations are what are called gravitational waves, and they are caused by very cataclysmic collisions, very strong gravitational collisions, and only then this grid, this elastic grid, can be shaken up. And the reason, actually, you can compute this, that this grid is stiffer than steel by a factor of 10 to the 20. So it's very, very stiff, and only very, very strong objects or events can shake it up. And this happens in the universe, and we first observed it in 2015. I'll come to that a bit later, actually. Okay, but this is the idea of the general theory of relativity. Okay, that space-time is a grid which is bent by heavy objects. Okay, so now let's go to another very important implication of the general theory of relativity. Just wait a minute, I need to drink something here. Okay. So, time in general relativity. So Einstein's theory implies that time flows differently for two observers in a gravitational field. Now, what do you mean by that? I'll explain that to you. You see, if you are near the Earth, near a large gravitating object, or if you are further away, your clock will show different readings. So if you're very near the Earth or any other large gravitating object, the clock will slow down. So for example, if you're 100 meters apart, the change is only 1 part in 10 to the 15. That is why we never notice anything. That is why all our watches read the same on top of the Empire State Building or on the ground below, right? Nobody sees a change of time, right? Because the factor is so small. Now, however, if you are, for example, in a satellite which is, many hundreds of kilometers above, then this makes a difference. And in fact, I just wanted to mention that this effect is extremely relevant for the global positioning system or the GPS. And all of us have cell phones, and we use them to find out, how to go where, and, we can track our motion, all that. And that accuracy depends upon taking into account general relativistic corrections, and also corrections of special relativity, because the satellites are moving at very high speed, okay? High and a high speed. So it's quite amazing that general relativity has a practical implication, which we are all sort of using all the time, okay? But this is a very deep fact. And after making a very long story short, just wanted to tell you how Einstein's equations really look like. You can just imagine it as some beautiful piece of art, but I cannot explain these to you unless one has some knowledge of differential geometry and stuff like that. Okay, but these are equations for this fellow G mu nu, for the metric. Just like Maxwell's equations are equations for electric and magnetic fields. Huh? And you notice that this gravitational constant, Newton's gravitational constant, and this is the speed of light. And if you calculate it, it's of the order of 10 to the minus 43 in some appropriate units. And this is the reason why the gravitational grid is so stiff. This is the reason for it. Okay. Now, let's go ahead. So this is I explained to you Newton's theory and weaknesses of Newton's theory. Then we went to Maxwell and Maxwell's equations, their experimental verification, and their implications for the structure of space-time, and then the geometrization of space-time by Minkowski, and then the resolution of the problems of Newtonian gravity within special relativity, giving rise to the general theory of relativity. So we are at the general theory of relativity that's 1915. Okay. So we traveled many hundred years already. All right. So now let me discuss one of the important implications of the general theory of relativity. There are several of them, but I cannot discuss all of them. But let me just do this. Okay. So general relativity predicts black holes. They were found just a year after Einstein's theory by Carl Schwarzschild. And they are solutions of Einstein's equations. And what I'm saying over here in this slide was realized only decades after the discovery of Schwarzschild. That these solutions basically divide space-time into two parts. There's something called a horizon. It's a black hole, divides space-time into two parts. One which is outside the horizon, the one that is the space-time which is inside the horizon. Okay? And this horizon, this surface, which in 3 dimensions is just equivalent to, or topologically a sphere, hides or clothes a singularity where the gravitational field blows up, and we really don't know what the laws of physics mean there. Okay? All right. Now, the interior and exterior are separated by a surface, as I said, called the horizon. This is called the horizon of the black hole. And even light entering it cannot get out. So if you fall in, you cannot get out. Okay, so that's a prediction of general relativity. And the nature of the surface called the horizon. And hence it's called a black hole. And this name, I think, is due to John Wheeler, that, light falls in but cannot come out. Classic. The black hole spacetime has a curvature singularity, as I said, and inside the horizon, the radial direction is time-like. And this is a little bit of a mathematical thing that if you continue the solution of the Einstein equations beyond the horizon in certain coordinates, then space and time interchange their roles, and falling inside essentially is equivalent to moving in, time falling into the singularity in time. And in some sense, we can say that time ends at the singularity. Okay. So one of the reasons to study black holes, one of the reasons so thoroughly from a theoretical point of view, is because we would like to understand the singularity of the involved in cosmology, about the origin of the universe and stuff like that. And so this is in some sense falling into the singularity in time. But if you reverse it, it's like coming out of the singularity. That's more of a cosmological type of model. I mean, these are just pictures, okay? In equations, these things are more complicated, but it's good to have a picture and a motivation for why we are studying these type of things in general relativity. It's one of the reasons. Then I just wanted to mention that the fact that Einstein's equations have black holes generically was, sort of shown by Roger Penrose in 1973, and he got a Nobel Prize a few years ago for this discovery. Okay. It's a robust prediction of general relativity. Okay. And the horizon, as I said, is a null surface. And this null surface has a certain characteristic radius, which is given by 2 times the Newton's constant times the mass of the black hole divided by the square of the speed of light. And this radius, this object, which has the dimensions of distance, is called the Schwarzschild radius. Okay. And so, as I said, the horizon separates the black hole into a region which is exterior, in which r is greater than the horizon radius, and a region which is interior to the black hole. Now, the important point is, therefore, that there is a radius square which you can calculate, and from there you can calculate the horizon, the area of the horizon. Let's say if we are in, let's say, 3+1 dimensions, then you know that the area of the sphere is 4 pi r square, and you get this very important quantity called the area of the horizon. Okay. I'm just telling you the facts. Okay, I'm not giving you any derivations, because all of that will take a course to be delivered to. But then you can look at some good textbooks and figure it all out. Actually, okay. Maybe the textbook of Sean Carroll is a very good one to study some of these things. Okay, so let's move on. So again, the flow of time in the presence of a massive star and a black hole. Remember, I had this cartoon of 2 people on different floors and how time sort of moves faster for the person who is on the top floor. The same thing. And the flow of time is basically, measured in terms of this particular quantity, 1 minus the horizon radius divided by r. So if r is very, very large compared to the horizon radius, that means you are far away in the exterior, then you see this factor is 0. So there is no issue actually. So however, as you go nearer and nearer to the horizon, you see this time actually just slows down. This is the same thing I told you before, that if you are near a massive object or which has a strong gravitational field, then the clocks will all slow down. And they slow down by this factor. Okay. All right, good. So now let's replace the star by a black hole. So this is one way of describing the black hole also. That, this is the observer's clock very far away from the black hole. And then you sort of track the timekeeping device as you go nearer and nearer and nearer to the black hole. And then when you reach the horizon of the black hole, the time stops. It just freezes. So this is one way in a certain set of coordinates to describe the notion of the horizon of a black hole. Okay. So I just wanted to bring out some physical properties of a black hole, and explain it in pictures, and especially the role of the horizon and what happens to time. Okay, let's go on. So this is still classical general relativity. This is all theory. However, very nice. When I used to give these talks, let's say 15, 20 years ago, we always used to say that astronomers believe that black holes exist, and there's so much indirect evidence. Today, we can see it. Here it is. So this is the first image of a supermassive black hole and its shadow in the Messier 87 galaxy in the Virgo cluster in the sky. And this was observed by the Event Horizon Telescope in 2019. And the key point is that no light was observed coming from the line of sight, indicating that there is the idea of a horizon is there, indicating a horizon in the theoretical description of this object. So This is direct observation, but black holes have also been indirectly observed in the galactic center of our galaxy, Milky Way, by Guess and Genzel, for which they got the Nobel Prize, and also by the observation of gravitational waves by LIGO, which I will now turn to. I'm just giving you evidence, experimental evidence for black holes, and why all the theoretical studies that we used to do for maybe almost 100 years or less, slightly less than that, is coming to a certain fruition, because now we are observing these objects by our instruments. So here is a cartoon of two black holes. So this is I'm trying to describe to you the event which was observed in the September of 2015. So two black holes, approximately 1.3 billion years ago, approximately, collided. So black hole 1 was approximately 36 times more massive than the sun, and it had a horizon radius of 210 kilometers. This stuff is all real stuff. It's not it's not theory or imagination. And this black hole was approximately 29 times more massive than the sun, with a horizon radius of approximately 170 kilometers. So these two black holes spiraling around each other, coming closer and closer and closer, and boom, they become one black hole, and with a different mass. And just 1 minute, I was hoping that there was an animation here, but it's not working. Then these two objects, when they collide, they settle down to a single black hole. Okay? So post-merger, the residual mass is 62 solar masses, which is 3 less than the sum of the masses of the original black holes. So 3 solar masses of energy was radiated in terms of gravitational waves, which were observed in 2015 by the LIGO observatories in the United States. This is quite a momentous discovery, and it confirms our faith in the general theory of relativity and its predictions at large distances. Okay, so this is quite amazing. So now I go back to theory again. Okay, now that they exist, we have even more motivation to study the problems they create for theoretical physicists. And so let me start with. I'm now going to tell you about the work of Hawking and all the other people at that time. By Hawking, I mean somebody who characterizes an epoch. There are hundreds of people who contribute in science, but we use 1 or 2 names only. Similarly to Maxwell's theory, I said, but lots of people contributed to that. The point is, I cannot say that about Newton. I think he was just, what shall I say, was just came out of the blue. Nothing before. It's incredible. But anyway, I will now discuss with you the consequences of Einstein's equations of general relativity. The following. So if you have one black hole and another black hole, and they merge, okay, so you get a bigger black hole plus radiation. Now, one of the big theorems of general relativity, which was proved by Hawking and many others, is that the horizon area always increases. Now, if the black holes are simple, whose horizon radius is, given by, it's proportional to the square of the mass, right? The area is proportional to the square of the mass, right? So then it's just a simple thing that m1 square plus m2 square is, of course, less than m1 plus m2 whole square. It's as simple as that. But in general, how to prove this type of theorem is not trivial. And these are so famous area theorems of general relativity, that when two black holes merge of any type, the resulting black hole always has a larger area. Okay. Now, this is a theorem of geometry. All right. That's very interesting. Now, in 1973, Bekenstein, who was a student of John Wheeler, introduced a very remarkable idea. He said that take a hot object and throw it into a black hole. It disappears, right? So you just imagine classical general relativity. There is a black hole, there's a horizon. Throw a bucket of hot water inside, all right? Now that bucket disappears, right? So it disappears means that the entropy of the water.
Professor, you are muted. No.
Hello, Prof.
Okay.
Yeah.
Okay.
Now it's okay.
Yeah. No, it is just all these slight touches here and there that do all these things. Sorry.
Okay.
Apologies. Where was I?
Yeah, you were about the increasing entropy of the black hole.
Right. Okay. So now Bekenstein noticed that there is a problem with the second law of thermodynamics unless you assign an entropy to a black hole. And he made a proposal that the thermodynamic entropy of a black hole is proportional to the area of the horizon. And clearly, that would be consistent with the second law of thermodynamics, right? Because as I explained to you, if you have two black holes merging, then the residual black hole has a larger area of horizon, therefore larger entropy. So entropy increases in this process, right? So it's consistent with the second law of thermodynamics. And so he made a very, very profound discovery about the nature of classical black holes, that you have to assign an entropy to it proportional to the square of the area of the horizon. I'm sorry, proportional to the area of the horizon, so that the second law of thermodynamics is still valid. All right, so this is what I have said over here, that the area theorems imply the second law. And in fact, it's not only the entropy of the black hole, but also the entropy of all the radiation that goes out and all the stuff outside, right? The total entropy has to increase, okay? And the proof of the total of the fact that this so-called generalized entropy formula, which is S black hole plus S matter, which was proposed originally by Bekenstein, was proved only very recently, within the last 10 years, by Alan Ball, actually, so using theorems of general relativity. So the basic point is that when a hot water bucket falls into a black hole, the matter decreases because the bucket is gone, but the entropy of the black hole increases by more. The entropy of matter is gone, but the entropy of the black hole increases by more, so that the generalized entropy always increases. Okay, so this is a very important point, that black hole physics is consistent with the laws of thermodynamics. All right. Now I will change gear, and I come to explaining to you very briefly in a few slides quantum mechanics. So before that, I just thought of giving you some idea of the type of scales of length that we are working with within our observable universe. So the observable universe is approximately 10 to the 28 centimeters big, whatever we have in our experimental observation. And this observable universe, I mean, the question is how small the distance I have been able to observe in the laboratory, like the CERN laboratory in Geneva. And that distance is of the order of 10 to the minus 16 So we have this huge span from 10 to the minus 16 to 10 to the 28 centimeters. It's a huge expansion. This is somehow, in a sense, the dimension of our universe, of the universe we have observed. Of course, we expect distances to go all the way to 10 to the minus 32, which is called the Planck length. In the physics over here, we do not really understand or are able to observe. And so this is the arena of what people in string theory work on. They want to understand this. Among other things, understand distances which are, near about the Planck length. Okay. So this is about scales, and this is about further ramification of what I said. This is approximately the radius of our galaxy. This is the Earth to Sun distance. This is the radius of the Earth. This is the size of atoms. This is approximately an angstrom. And this is approximately a Fermi, 10 to the minus 12 centimeters. And this is what we have been able to reach in the high energy physics experiments in CERN. It's quite amazing. No? Now, so this tells you, it's another picture basically. So distances of 10 to the minus 16 are being probed at the Large Hadron Collider at CERN in Geneva. And these are astrophysical, experiments actually that look out at the sky. And the latest ones are like the James Webb telescope, and it's amazing stuff actually that's going on in experimental science, especially in astronomy. So I see some pictures of the scales involved. Okay, matter. So this is matter, ordinary matter that you are sort of very familiar with, and molecular structure. Molecules are made of atoms. Atoms have electrons and nuclei. Nuclei have nucleons like proton and neutron, and those are made up of quarks. So we are trying to explore this universe of ours, at all these scales. And in some sense, this is a symbiosis of particle physics, astrophysics, and cosmology, this whole huge arena of length scales, how to say it nicely, actually. We are exploring the universe from very, very tiny scales to very, very large scales. And we'd like to have an understanding of all of this phenomena within a single framework of physics, actually. So this is the big challenge. Okay. All right. So this is what we want to understand, what we want to do. And general relativity essentially has helped us organize a lot of experimental data in the universe at large, actually, and in at cosmological scales. But the laws of nature, actually, the Newtonian laws of nature do fail at the scale of atoms, molecules, and that led to the discovery of quantum mechanics almost 100 years ago, in 1925. I think Heisenberg's paper is in July of 1925, if I remember right. And in these 100 years, we have understood amazing things about nature at a microscopic scale, and which has revolutionized life on Earth for us. So this is just a cartoon of this thing, which I'm just trying to tell you that. Let me read out this thing over here. If the proton and neutron in this picture were 10 centimeters across, okay? proton and neutron. That is this object, this bluish object. Then the quarks and electrons would be less than 0.1 millimeter. These are the quarks, these are the electrons. And the entire atom would be 10 kilometers across. So you see the scale, the atom is mostly empty. And this was a great discovery of Rutherford, this type of structure. Okay, so quantum mechanics is the theory of microscopic particles. It modifies classical equations of Newton, and it's the basis of electronic devices, lasers, collisions, colliding elementary particles, and they all follow the laws of quantum mechanics. And it has been tested till 10 to the minus 16 centimeters, okay? And quantum mechanics also has led to macroscopic effects like the explanation of superfluidity, superfluid helium, etc. What I'm trying to say is that in the last 100 years, quantum mechanics has established itself as the fundamental theory of the world. That doesn't mean that we, in the future, will not discover phenomena which quantum mechanics will only describe approximately, and there may be a new law of nature. You can never say that. Okay, so now that I've talked about general relativity and quantum mechanics, let us try to put them together, and that is where all the fun begins. There's a big problem of the compatibility of quantum mechanics and general theory of relativity. So I just want to now briefly talk to you about the work of Hawking, who I think was the first person to try to study the implications of quantum mechanics for gravitating objects like a black hole, for example. So in one of the celebrated calculations of the second half of the 20th century, in 1974, Hawking discovered that black holes radiate due to quantum effects. They are not black because radiation that was not coming out comes out due to quantum effects. Classically, there is no such radiation. And he calculated the temperature of the black hole and found his famous formula, which is actually on his tombstone. That the temperature of a black hole of the type Hawking worked with is given by this formula. It is inversely proportional to the mass of the black hole, but very, very importantly, has this factor of h bar, which is a constant that comes from quantum mechanics, actually, right? This is the famous formula of Hawking. And if you, for example, calculate the temperature of a black hole of the mass of the sun, okay? The mass of the sun is something like 10 to the 30 or 33 grams or something like that. You just put that into this formula and you'll get a temperature which is very, very low, 10 to the minus 7 Kelvin. But if you look at a black hole of the size of the Earth, mass of the Earth, sorry, what happened? Yeah, then the temperature is 0.1 Kelvin. And now even if you go to lower masses, like 10 to the 18 kilograms, then it's 7,000 degrees Kelvin. These are very simple thing to calculate given this formula. It tells you that, as the mass decreases, the temperature increases actually. And these are some precise numbers to illustrate the main formula. And the fact that this black hole is no more black, then it becomes some sort of a white hole, right? Because the temperature is so high. And now with this formula, this famous formula for temperature, Hawking calculated the entropy of the black hole exactly. And actually the main number over here is 1/4. It's not 1/2, it's not 1/3, but it's 1/4. And it comes from this formula, which is calculated because there's a big calculation that gives this formula. So if you put this in over here and use the first law of thermodynamics from this formula, you get the entropy formula. And this is a celebrated formula of physics of the last century, Bekenstein-Hawking formula. And you can notice over here that the C cube divided by h bar g, okay, essentially is what is called the inverse of the Planck area, right? So this formula says that it's the area of the horizon divided by the Planck area times 1/4. So that's the famous result of the black hole entropy. All right. Now I think some parts of this talk will be a little more technical, but I'll just mention these things for you, okay? Just these statements. How they are derived, I will not get into at all. Otherwise, we'll never finish. The formula for the black hole temperature and entropy is universal and independent of how the black hole was formed. This is a very important point. Okay? This is because the answer at late times depends, well, this is the technical reason, on very high energy Hawking quanta that emerge from near the horizon of the black hole after the collapsing matter has crossed into the horizon. So I'm not going to explain all that to you. And the radiation appears to be thermal because we are not keeping track of the part that is on the other side of the horizon and which is in some sense entangled with the radiation we are observing. So the black hole is radiating, and this radiation is thermal. And it's thermal because we are not keeping track of what's happening inside the horizon. We're just looking at the whole system from the outside like a thermodynamic system. And that is the problem. Because now you will say that, there is information loss because a black hole is formed by some collapsing matter. And this collapsing matter, is in some quantum mechanical state, some given state, and it collapses and forms a black hole. And then the black hole starts evaporating. But what comes out is thermal. Now, that is not allowed by quantum mechanics. The laws of quantum mechanics tell you that the wave function evolves in a unitary fashion by some Hermitian Hamiltonian, and sort of probabilities are conserved. So this is what is called a information puzzle, which Hawking's 1974 calculation brought to light. Okay, a black hole forms in various ways, but it always evaporates in the same way into thermal radiation, leading to information loss, as there is no memory of the initial state. And this violates, as I said, a fundamental principle of quantum mechanics, that a pure state, evolved into a mixed state. Hence, there is a serious problem. So general relativity leads to information loss, and quantum mechanics cannot allow it. So this started a very big investigation into how to resolve this problem. And in the resolution of this problem, we have, over the last several decades, almost half a century, learned how to. We have learned a lot about gravity. Somebody saying something?
Yeah, I'm extremely sorry to cut you, Professor, but as you mentioned, even if we analyze the entire radiation coming out of a black hole per se, even then after that also we cannot analyze what happens or what will happen inside the event horizon.
No. I think that is not true. If you are able to keep track of what is coming out in conjunction with what went in, this is a very long, big story. If you can do that, then there is good unitary evolution. There is no problem.
So that may be an approach to the information paradox.
Yes, and that is what people have been working on for the last several decades. And in the last couple of years, this type of idea has been sort of fruitfully understood, means there is good understanding of how to sort of recover information from the radiation, and how black hole evaporation is consistent with the laws of quantum mechanics. So, I mean, I don't think that this has been rigorously understood in the sense of mathematical rigor, but physically we have a pretty good idea as to why black hole evaporation can be understood as a unitary process.
Oh, yeah, please continue.
Okay. Yeah. So I just wanted to give you some summary of. So black hole thermodynamics, since black hole is a thermodynamic system, can information loss for black holes be understood as due to an averaging process of many internal states, like in usual treatment of quantum statistical mechanics? So if a piece of coal is burning or some wood is burning, you don't say that there is some problem with quantum mechanics, right? Nobody says that. So, and this is because we understand information loss statistically in terms of quantum statistical mechanics. And which is, I'll just very briefly mention this extremely important point, that is it possible, therefore, to understand black hole entropy in terms of Boltzmann's law? Means like we describe the burning of coal, or burning of, or the operation of engines. There is entropy loss, there is radiation. Do we jump up and down saying that there's a problem with quantum mechanics? Of course not. The reason is that we can explain all of that in terms of the ideas of quantum statistical mechanics. And the key sort of, what shall I say, understanding is the idea of entropy in terms of the logarithm of the number of states of the system. And the question is, can we understand black hole entropy in terms of Boltzmann's formula? What are the internal states of the black hole that could account for the black hole entropy? So this is a cartoon which I'm saying that this is a black hole. Is it equal to some complicated system like the stuff that made of matter? And is it possible that we can understand the laws of thermodynamics and for black holes in terms of quantum statistical mechanics? And in many special cases that we can analyze, the answer is yes. So I'll just, this is a slide of work, a very important work actually, which say the answer is yes, that there are black hole microstates, and you can calculate the entropy of these microstates and show it equal to Boltzmann's law. You can also calculate Hawking radiation in such models and show that it is consistent with Hawking's calculations. You can do higher order calculations of black hole entropy in string theory, which was pioneered by Dabolkar and especially by Ashok Sen and others. And somehow, my main point is that if we understand black holes in general relativity in the framework of string theory, then in the framework of string theory, we can understand black hole entropy in terms of its microstates. And these microstates in certain models which you can understand are made up of D branes. These are like the atoms of space-time or some picturesque way of talking, I'm just saying. Okay? But this can be calculated very precisely. And these are called D branes, which are, domain walls of string theory. I mean, these are solutions of string theory, which are like domain walls, and made of these, we can wrap them around, put them together to form bound states, which can sort of, form an approximate description from the outside of a black hole. And then we can account for black hole thermodynamics and Hawking radiation from such a model. And of course, these models depend a lot on supersymmetry, because otherwise we can't calculate But it's quite amazing that in a large class of models, supersymmetric models, in which the calculation can be controlled. I won't get into these details due to some non-renormalization theorems of supersymmetry that we can realize black hole thermodynamics in terms of these microstates. Okay. Now, all of this discussions basically led to a very great discovery of what is called the holographic description of quantum theory, of string theory, and hence string theory of quantum gravity. So you see all of these explorations about the entropy of black holes in terms of microstates involved looking at D branes and their excitations. And the excitations of those Z branes are described in terms of some non-abelian gauge fields. And this is a very beautiful story, actually. And Juan Maldacena realized, actually, in 1997, that what is today called the ADS-CFT correspondence, that if you look at quantum gravity or string theory in what are called asymptotically anti-de Sitter spacetimes. So anti-de Sitter spacetime is basically a spacetime which has a boundary, and it's like a gravitational box, So whatever is happening inside the box, gravitationally or string theory wise, in principle is coded on the boundary as a hologram. And the theory on the boundary is familiar type of theories that we work with, which are called non-abelian gauge theories. So this was the great ADS-CFT conjecture of Juan Maldacena, which now has been sort of worked upon in the last 20, 25 years, and with enormous amount of progress and understanding. But as always, there's just so much more to do, actually, to really understand this problem. So it's just a cartoon. All gravitational phenomena has some sort of a hologram. And this picture over here basically shows you a black hole and matter around the black hole. And that is described by some sort of a gauge theory on the boundary of ADS, which is at a certain temperature, which reflects the temperature of the black hole. So you want to study black holes very well, then you can simply study this theory. And so in principle, we know that because this theory on the boundary is a unitary theory, there is no information problem in principle, but you've got to work it out. And I think a lot of, what shall I say, effort has been to sort of work out this basic point that if there is no information loss on the boundary theory, how is it reflected in the bulk? Okay. So this is just all simple illustrations of what I was saying. So this is your gravitation theory in the interior. The boundary is the ADS spacetime, and whatever happens in the interior is coded in these blue beads, which are degrees of freedom on the boundary. Okay. So on the boundary lives a unitary theory. So this is a simple illustration of ADS-CFT. Now, what about finite temperature? So if you have a black hole, it means that the theory on the boundary is at a finite temperature, basically. So temperature and entropy of the black hole can be understood in terms of the motion of particles on the boundary, of hot particles on the boundary. Okay. And in principle, this solves the information puzzle, as I said, because black hole formation then is just thermalization of the theory of the boundary. And after this ideas came into, some acceptance, Hawking considered that there is in principle no information loss. So this is a really deep development, but we got to sort of figure out how this all works actually. So I have now several slides. I don't know whether I should go into them because how much time do I have now?
Yeah, like, no, you can take as long as you want. The time bound is not an issue.
Okay, I have just a few slides. So I just go through them because they are a bit dense, but I just want to give you an idea of there is a certain connection of trying to understand black hole physics, black hole information in terms of the language or physics of information theory. Okay, so I just want to, just give you a very sort of a, what shall I say, a sketch of that. So there is recent progress in answering this question, as I've said. It involves understanding information laws as quantum information laws and uses concepts of information theory. In particular, the concept of quantum entanglement and its measure by the so-called fine-grained entropy or the entanglement entropy, which was introduced by John von Neumann in 1932, and its geometrization by Ryu Takanagi and many others. So what people found the last several years is that there's an old paper of Don Page, a student of Hawking, that is a good, what is called a Page curve is a good diagnostic of the time evolution of the entanglement entropy of an entangled composite quantum system. Okay. So you can imagine the evaporating black hole is a composite system. You have the black hole degrees of freedom and there's radiation. And how does the entanglement entropy sort of scale with time in a unitary theory? So Page gave that diagnostic. Okay. So I have a slide here on what entanglement means and about the density matrix. So I'll just very quickly go through it because this is very important. This is very elementary quantum mechanics actually. So, okay, just bear with me. So consider you have two systems A and B. Okay. This is system A, which has two states. And this is a bell pair, as people call it. The system B and the system C, which is a product system. The states here of C are products of the states here. So there are four of these. The dimension of C is 4. No? You can form 4 states. So we can consider separable product states like this, as I mentioned, like take 0 from one and 1 from the other, and in which both systems A and B are in a definite state. However, if you take a state like this, it is not a product state. And this state is called an entangled state. It does not belong to either A or B. This is a very important, beautiful point of quantum mechanics, that there are entangled states which, in which the degrees of freedom are entangled. And you cannot say that the system is in either state A or B. Okay. Now, how do you mathematically sort of assign some measures to this idea? And this has to do with the idea of a density matrix. Okay, so density matrix for a product state is given by just this bracket. Just the Dirac bra and ket. And since this state is normalized, we have rho square equal to rho. This is a very important equation. For pure states, rho square is equal to rho. Now, in case you don't want to observe the system B, okay, so for example, you don't want to observe radiation inside the black hole. I mean, just illustration I'm saying. we trace over the states of the system B. So you trace out B in this density matrix and you call it rho of A. And this is a reduced density matrix. And it turns out that rho square is not equal to rho. Okay. So the idea of entanglement says that basically, if you have a complicated entangled system, and if you trace out one set of degrees of freedom, then rho square will not be equal to rho. Okay. And von Neumann entropy is a measure of this type of, what shall I say? Distinguishes between rho square equal to rho and rho square not equal to rho. Because if you define an entropy like this, minus trace rho log rho, with trace of rho equal to 1, then if you have a pure state, you can prove that this is 0. Because rho square is rho, the eigenvalues are either 0 or 1. And this object is always 0. But if you have traced out some degrees of freedom, you have the reduced density matrix, then the von Neumann entropy is not 0 actually. Okay? And there are some very beautiful, simple statements about the von Neumann entropy of a subsystem A is the same as the von Neumann entropy of the subsystem B. And the von Neumann entropy does not change under unitary transformations. Okay, so it's an invariant of time evolution, unitary time evolution, and it's bounded by the Boltzmann entropy. That is why there's a distinction between thermodynamic entropy and von Neumann entropy, where the n is the dimension of the Hilbert space of the system. So, all right. So all these are some very beautiful, simple statements, very important statements you can derive just on pencil paper. So for a bipartite system like A cross B, the entropy of the union of this is always less than or equal to SA plus SP. And remember, this is extremely different from the thermodynamic entropy, which is the opposite. Remember? If you take two systems and you combine them, the entropy of the final system is always greater than the sum of the entropies of the individual systems in the usual Boltzmann entropy. But for the von Neumann entropy, it's exactly the opposite. And okay, I just wanted to just point this out to you, which is very different from the thermodynamic entropy, but the entropy of the combined system is greater than or equal to the entropy of the paths. And all this was sort of, put together. I'm summarizing the result of a large amount of research by a large number of people, and I have named none of them here, but you can easily find it in the literature. That this is the page curve of evaporating black hole. So you have an initial state in which there's a black hole, certain entropy, and there's radiation happening along the red curve as you go up in time. So this is time on the x-axis, okay? And on the y-axis is the entanglement entropy. So at some point, the radiation entropy and the entropy of the black hole agree with each other. But Hawking's calculation is the blue line, that the entropy of radiation will keep on increasing. And that is corrected actually by a correct quantum mechanical calculation to show that the entropy, this curve, the red curve, actually then bends down and goes to 0 in the final state, because the entanglement entropy in the final state has to be equal to the entanglement entropy in the initial state. And therefore, after a lot of effort, actually, people have been able to understand the black hole evaporation as a phenomenon in a unitary theory of quantum reality, when quantized matter interacts with a black hole. So I just wanted to say that this is the last slide, and I have two more slides which I want to make some general comments now. So I just wanted to point out to you that this is a picture of the sort of problems that we would like to understand, and a lot of it is understood, but not everything. So this is the so-called Big Bang here. I mean, supposedly at Planck time and Planck distances, for which we have absolutely no theory. We don't have a theory of how the universe began or whether there was another universe before it, and sort of, it's like an hourglass type of thing, that there was a universe that contracted, and from that contracted universe began our universe. We have absolutely no idea of all these things, but we have a fairly good idea of physics from here. So I just wanted to show you a cartoon of the time scales in the evolution of the universe, the formation of galaxies, and here we are in a very cold universe. Cold in the sense of the cosmic microwave background radiation is very, very low, approximately 2.76 degrees Kelvin or something. And so this is the sort of big picture of the type of physics that we'd like to understand. It involves everything. And I want to end with a very interesting quote which I came across. So it says, the most amazing is this realization that everything that exists in the universe came from a common origin. The material of your body and the material of my body are intrinsically related because they emerged from and are caught up in a single energetic event. He's referring to the Big Bang. Our ancestry stretches back to the life forms and into the stars, back to the beginnings of the primeval fireball. This universe is a single multiform energetic unfolding of matter, mind, intelligence, and life. And all this is new. None of the great figures of human history were aware of this. Not Plato, nor Aristotle, or the Hebrew prophets, or Confucius, or Thomas Aquinas, or Leibniz, or Newton, or any other world maker. We are the first generation to live with an empirical view of the origin of the universe. We are the first humans to look into the night sky and see the birth of stars, the birth of galaxies, the birth of the cosmos as a whole. And our future as a species will be forged within this new story of the world. I just thought I'll end with this quote. So thank you very much.
Yeah,
We've exceeded the time quite a lot, but
okay. But the quote was extremely amazing. So, like,
yeah,
we have a few moments for the Q&A, I think.
Sure.
So yeah, there is a question. Will the entropy of a black hole also increase as the black hole sucks or attract the light?
Yes.
Okay.
Light is like any other form of matter, no? I mean, because it doesn't have any mass, but it has energy, right?
Yeah.
So it's energy falling in. So the energy falls in, that means the mass of the black hole goes up, and therefore its entropy goes in. That's quite simple.
Okay, there is another question. So, as per the Schwarzschild radius, we can perceive our own observable universe as it is inside a black hole. So, does this make physical sense, and does it have any implications? So, I think
it's not a black hole actually, but if you look at the De Sitter model of cosmology, what is called a static patch of de Sitter spacetime, then in a sense we are inside the horizon of that
Oh,
spacetime.
so not exactly inside a black hole, but we can perceive the
No,
boundary
no.
as an event horizon. We can't escape the boundary
Yes,
of the universe.
exactly. Yeah, in a certain what is called a static patch of de Sitter space. De Sitter space is a solution of Einstein's equations with positive cosmological constant.
Constants, yeah.
It's this expanding universe, and there's a static patch in which there is a horizon, and in that framework, we are within the inside the in the
Okay.
interior. Yeah.
Yeah. Oh, yeah. There's another question. So, as we get closer to the event horizon of the black hole, time will dilate and will perceive the less time. Does black hole perceive time as well? Because black holes will eventually be affected by time and radiate finally. So, I think what this question
Black
is
holes.
trying. Yeah, it majorly asks like, does black hole perceive time as well? Like,
But black hole, what do you mean by black hole? Perceived time. Perception of
times.
time has to do with an instrument. You have to have some instrument that measures time. And what I said is that for an outside observer, if you take his clock and move it near the horizon of the black hole, the time slows down basically almost to zero. That's all.
Yeah, because like we don't know anything what happens beyond the horizon.
No, we know. I mean, of course we know actually. So the big thing is that you can actually talk about the time of the infalling observers. And for that, you have to go to a new description, a new coordinate system to describe the infalling observer. And these are called the Kruskal-Szekeres coordinates. So, this is just part of some very basic general relativity that if you want to really discuss the physics of the infalling observer, you cannot do it in the coordinates of the external observer.
Okay.
You have to make a coordinate transformation to what are called the Kruskal coordinates.
Okay, like there's another question like when two black holes get closer, they will merge. Is there any possibility they will revolve each other like a binary star situation?
Yeah, that happens. I mean, in fact, they started revolving around each other as a binary system and got closer and closer and closer and collided.
Yeah. So, like, is there a chance like the black holes never collide? They like revolve each other like eternally or to say for a very long time?
That may be possible, but because I mean, we are not falling into the sun, are we?
No? Okay.
Because we have a certain. But you see, if you're losing energy as you go around, then you will fall in.
Okay.
You see what I'm saying? The spiraling black holes are also losing energy. And if you're losing energy, you'll start falling.
Okay. So like in like maybe a longer duration of time, but the black hole's rating will eventually collapse.
Yes, of course. Yeah.
Okay. And like there's a question like as you mentioned, the space-time metric is 10 to the power 22 orders of magnitude stronger than steel. So does it mean it will take extremely large mass or an extremely high amount of energy at a confined space to make to bend the space-time? And does the same thing happens with singularity?
No, so that's what I said before that this
So I think yeah, like
no,
the
what I
think
said was
the
that collision of black holes was so energetic in some sense that it led to these vibrations of the grid of space-time, which you observed as gravitational radiation.
yeah, I think the question is mainly trying to ask it like the stress energy tension T mu nu at the current aspect of general relativity, it like at singularity T mu nu blows up to infinity. So
Yeah,
like
but I was not talking of singularities
yeah,
at all. I was only talking of physics outside the horizon.
outside the black. So I think
Yeah,
the question tries to ask what happened to the space-time metric at the singularity.
I don't know.
Yeah.
We
think
get
no.
another black hole, and I don't know what happens there.
Yeah, that's an unanswered question. So, like, there is one last question. What is the boundary of the universe? If our universe is bounded, is it that possible? And lastly, our universe has a does our universe have a boundary or not?
I don't know. As of now, it seems that we have a open universe, but this
Okay.
depends upon observations.
Yeah. So like universe is expanding, but we don't know, have no idea of whether it has a boundary or not.
Yeah, we don't know. And I mean, what the fate of the universe will depend upon more experiments, like the Daisy experiment may indicate that the the energy density of the universe might be decreasing in time. So we'll have to revise our models of cosmology.
And like okay, there's one last question, and I think that's also it says like the general theory of relativity is somewhat incomplete as we include the singularities and other things. So does we need to like improve general relativity on itself, or we do need to move on to another theory of gravity?
No, I think general relativity looks like, in its domain of applicability, it's a good theory. But if you go to very short distances, then it needs modification. And this is the proposal of string theory, actually, that would be the more fundamental theory. But all this is not yet completely worked out. And it's a theory in the making, actually, in some sense. Yeah. So we have good indication that this is the way to go, but there's a lot more to do.
Okay, so like at the end, I asked one question at the end. I'll ask sorry, I asked one at the beginning. I'll ask one at the end to the professor myself. So like, what do you have to say for the younger generation like us, like who are currently studying undergrad and graduate physics, and like look forward to like researching in string theory or in black holes or ADS-CFT correspondence? Like, what do you have to say to us personally? I think.
Yeah, what I would like to say is that I think you should, in my view, you should get a very solid foundation in physics, which is not only relevant for black holes or string theory, but a solid foundation in physics, which you know statistical physics, condensed matter physics, and all those areas, and some mathematical methods. You should you should be a good theoretical physicist, and then work in this very sort of more advanced areas, because you may need ideas from other areas in order to sort of make some progress in many of these things. So I think that you need a broad education, and please pay very special attention to experimental physics, and there's a great future in experimental astrophysics, cosmology, and all those things. In high energy physics, I think the new experiments planned will take many decades. But in astrophysics, there are just so many new telescopes and new probes that there's a lot of data will come, and it'll need a lot of understanding. It's really important to also pay attention to data and data driven, because it affects your ideas of the universe.
Yes, so I think that's all we have for this today. I'd really like to thank Professor for making the time to give this talk. And
yeah, okay.
Yeah, thank you, Professor.
Thank you.
Okay.